Hello, this is Dr. Jabbour, and today I'm going to go over membrane transport. So we already talked about the cell membrane, and we're going to see how the cell membrane allows for solutes to go through the edges of the cell and enter the cell or exit the cell. That's what we're going to talk about today. So the cell membrane is called the plasma membrane. And we describe it as being selectively permeable. Let me really underline this because it's very important. Selectively permeable. This is very important to know that because selectively permeable means that it will only selectively allow certain solutes to go in and out of the cell and not everything. So permeable means it allows for ions and solutes in general to go through, but because it's selective, it's not everything. Not everything can go through. So it allows some substances to cross more easily than others. And actually some cannot cross at all. And that will be the case of some hormones, and they will have to act on the cell from the outside because they will not be able to get inside the cell. There's no way in the cell for certain protein hormones. So small non-polar molecules cross the membrane easily without the help of transport proteins because they are non-polar. Non-polar molecules can actually blend through the membrane because if you remember, the membrane is rich in phospholipids. Phospholipids are a type of lipid. They're hydrophobic, and the phospholipid tails are facing each other, and it just makes a thickness for the membrane that is just very hydrophobic. So you need non-polar molecules. Only non-polar molecules can really blend with this type of environment. So if you are a non-polar molecule, you can actually go through the membrane, and if you are also small enough. So no help of any transport proteins. Now, if you are large or polar or charged, now you're going to need the help of a transport protein. And sometimes some polar molecules don't even go at all. That's why we say it's selective. But some polar molecules will be transported inside the cell, but it will require a transport protein that will allow them to cross this hydrophobic barrier because they normally wouldn't blend with the membrane. So they need a protein that literally kind of flip-flops through the membrane to let them go through, or tunnels. It will form tunnels to let them go through. We call them channels. So transport proteins to help cross the membrane. So they may be channels or carriers. And we're going to see both examples, so I'm not going to draw them right now. Here we go. So let's talk first about passive transport. So here are three types of passive transports, and you need to know all these three types. Passive transport will take place when we have more of a solute on one side of the cell than on the other. So we end up with what we call a gradient. Passive transport involves motion from high concentration towards low concentration of the object, the solute being transported, and the energy that drives them is just random thermal energy. So we go from high to low, and that's called a gradient. A gradient is a difference in concentration. So if we're going from high, well, it's not if, that's how passive transports occur. It has to go from high to low concentration. And that's the only way we have a passive transport. So why is that? It's because all these solutes are if they are in very high concentration in one compartment, they're going to have a tendency to go towards the other side to reach equilibrium, because that's the purpose of a cell constantly. It constantly wants to be in what we call homeostasis, in a state of a balance. And the solutes have to be equal on both sides of the membrane, and to be equal, you have to move. So if you're more concentrated on one side of the membrane, these solutes need to move to the other side of the membrane. And if they are small, like oxygen molecules, so this is a very small gas, it can actually diffuse right through the membrane and get to the other side. So this is a straight passive diffusion. So we use the term diffusion for a movement of, here we're talking about gas molecules, a movement of gas molecules, and here it's a passive transport, so it's a movement from high to low concentration. And this will not happen all the way until everything is moved to the other side. No, it will stop until we have equal number on both sides, until we reach equilibrium with equal number on both sides. And that's when it slows down, and eventually it just stops. So in reality, there's constant movement back and forth, basically to keep that equilibrium going. So here, this is passive diffusion. Now, when you are a charged particle, and this is quite, this is very polar, because you have an entire charge. This is even more polar than just a water molecule. The polarity at the ends of a water molecule. This is an entire charge. These are ions. This is an ion. So when you charge like that, that means you are polar. So if you're a polar solute, and so solute, the word is just a general term here. So here's the sodium ion. This is polar, and a polar molecule cannot form bonds with the hydrophobic tails of the phospholipids. This is a very hydrophobic environment in here in the cell membrane. All of this is very, very, very hydrophobic. So something that's polar is not going to just blend in there. Think of, the example I always use is, think of your big pot of water when you're getting ready to boil water for your spaghetti, and you add a little bit of oil in there just so the spaghetti doesn't stick together. But when you add that big drop of oil, it just doesn't just disappear in your water. It's a big fat droplet, and you might break it up with a spoon, and it will be very, many, many, many small fat droplets, but they don't just blend in and disappear. That's because oil is a lipid. Lipids don't form polar bonds with water molecules. So to allow for the passage of these charged particles, like an ion, you need to have a channel. So this is right here. This is basically a tunnel that is built with this protein that's embedded in the membrane. So you have, let me use a different color here. So this is, in blue here, this is a channel protein. This is a channel protein that's embedded in the membrane. It doesn't move. It doesn't just disappear, pop off, come back. It's just there in the membrane, and its job is to be a sodium channel. So when we need to transport sodium from outside the cell to inside the cell, or vice versa, we use that channel, because it cannot blend through the membrane and go through other than through the channel. So this is called a diffusion through an aqueous channel, and that's it. But the principle of going from high to low concentration, it's still valid for passive transport. We're still going from high concentration to low concentration. For some molecules that are just so big, like glucose molecules, they're just bigger, and they're charged, because the formula for glucose is C6H12O6. And as you know, most molecules with oxygen atom in them, they're usually polar because of those hydroxyl groups. OH, remember, OH groups, functional groups are called hydroxyl groups. These are polar groups that are, attached to the carbon backbone. and they give polarity to the molecule. So glucose is a polar molecule and it's big. So it's not an ion with a complete charge, but it's still a polar molecule. So it can't just blend through the membrane. It needs its own transporter. And the transporter that glucose uses is a type of carrier. So it's not specifically a tunnel per se. Glucose binds to a protein that's embedded in the membrane, and the protein stays there. And what happens is that this complex glucose and glucose transporter, as it's bound together, it think of it as flip-flopping through the membrane. Like, when you reach the end of a pool, you're swimming, you reach the end of the pool, and then you flip-flop in the water and turn around and go back to the other side. That's kind of how this complex turns in the membrane of the cell and allows the glucose to be released on the other side of the cell. And again, it's to allow the transport of glucose into the cell from high concentration to low concentration. So think of, for example, you've had a meal, you just had dessert, it was a pretty sugary meal. So you're going to have glucose molecule in your digestive system. It's going to be absorbed through the intestinal cells, get into the bloodstream, and then arrive to the cells. And that's how we feed our cells all throughout our body. And our brain cells need a lot of glucose. So when this glucose arrives to the surface of the cell, as it's being delivered to the cell, because the cell needs it for survival, it needs to get in the cell. And that's how the cell gets glucose in the cell with this transporter. So these are all types of passive transports. So these are examples. These are examples of passive transports. But don't forget the definition. The definition is from high to low concentration, and it requires no external energy in the form of ATP. So we don't really need extra energy to move these particles from one compartment to another. They're already, really concentrated and that they're randomly moving, and there's that thermal energy in that kind of like bunch, and that allows them to just kind of diffuse to the other side where there are less of them. And they're going to do that basically very naturally. It's kind of like when you're, shoving 100 students in a classroom that only has 50 seats and everybody's on top of each other. Nobody's happy. It's very crowded, very hot. You open the door, you say, oh, by the way, there's a classroom on the other side of the hallway, and it's happens to be available. And, everybody's happy. At least half the classroom is going to be leaving this very crowded classroom and go to the other side of the hall, and the students will be distributed across the two classrooms, and everybody will be more comfortable. That's basically what's going on here. When all these molecules are so crowded together, there's a lot of energy movement between them, and they'll have a tendency to move away towards a compartment where there's less of them, so they can kind of distribute equally. All right. So I spent some time on this one slide because it's really a very important concept. This is something that's going to, really be throughout all physiology in this class, and even in anatomy and physiology, this in your future classes. This is a very, very important concept. All right. So as we mentioned in the previous slide, some proteins are literally just channels with a hole in them where the particle just goes through it. And basically, the way this protein is that it's lined here with amino acids that happen to be polar. So this polar entity here, whatever it is, but in our example, they were sodium ions. So these are very polar, right? Ions are polar because they have a charge. That's the definition. So they need to go through a tunnel to get on the other side, because this is very hydrophobic, non-polar, the membrane. And of course, how can we make this possible? We would need the tunnel to be polar to allow for this passage of this polar ion. A carrier protein is more of a protein that will change shape. So it will grab the solute in question, and then it will change shape and literally release it on the other side. And that's the example of glucose transport. So how does this movement occur? The substances diffuse from where they are more concentrated to where they are less concentrated. And we literally use the words movement down, down a concentration gradient. So down the gradient. So whether we're literally moving physically from, let me go back to the previous picture here, or even here, whether we're moving from this side to this side or this side to this side, we're looking at the gradient. So here, the gradient high concentration happens to be up here. So it looks like we're moving down, vertically down into this low concentration compartment, that's how passive transports work. But sometimes in a cell, so if I continue the membrane here, there might be a very high concentration of another ion. It's actually an example we're going to see soon. Here's potassium. The cell has a lot of potassium ions inside of it and very little potassium ions outside of it. So there it is. You have a gradient in potassium ions with a high concentration on the inside of the cell and a low concentration on the outside of the cell. So if you're asked in what direction will passive transport occur, what would you say? This is where I encourage you to just pause the recording and think a little bit about the answer before I say it. Passive transport will take place from the inside of the cell to the outside of the cell because it goes down the concentration gradient. The gradient is high here and low up there. So we go from high to low. That's what we're talking about when we say down the gradient. The gradient is here from high to low. That's the gradient. There's a difference in charges. So what is the direction? It's high to low. If high happens to be inside the cell, then we're leaving the cell. If high happens to be outside of the cell, then we enter the cell. So whatever that gradient is, we're going from high to low. So when we see down the gradient, that doesn't mean down into the cell. It just means that from high to low. All right. So in those examples here, we have basically like a big beaker with solutions on both sides of a membrane that separates the two sides here. This is like an artificial membrane. So here we're going from right to left or left to right, but we have to look at the gradient. Where is the high concentrated compartment and the lower concentrated compartment? And we look at the solute, where is it in a high concentration? And we see where is it going to move towards. So diffusion across a membrane is called passive transport. No energy required. So here, there is a diffusion from these solutes that are so concentrated on the left, and they're going to want to move, and eventually they move to the right, and until equilibrium, right? Not until they all move to the right. No, it's until equilibrium is reached between the two sides of this artificial membrane in this particular kind of beaker. Like imagine there's like this big beaker here, and we put a membrane in the middle. Or you could just think of the cell membrane is here, this is outside, this is inside. Okay, so small, non-polar substances passively diffuse across the membrane via simple diffusion, no transport proteins needed. So net diffusion here is through the membrane. Now, this example, let's call it A. This was just one solute going from one side to the other. In this example B, we have two solutes in this drawing. We have the orange ones here and we have the purple ones on the right. So if you were asked a question about what's passive transport, what is the passive transport of the orange molecules, you have to look at the orange molecules. What side are they more concentrated in? What side would they be moving towards? And you would say it's a passive transport for these orange molecules. I see all these dots on the left. I see 0 dots on the right of orange molecules. That means they're high on the left, low on the right. So they're going to move from high to low. So they're going to move for the orange molecules. They're going to move towards the right side of that setup here. If you're asked what is the movement of the purple molecules here in this drawing, then you will look at the number of purple molecules. You'll say, oh, I'm looking here at the drawing. I see all the purple dots on the right side, no purple dots on the left side. Then by passive transport, they're going to naturally have a tendency to want to go towards the side where there are less of them. So that would be towards the left. So for the purple molecules, they're going to go towards the left. So if you're ever asked about studying a scenario like this, it'll be specific. It will ask you what is going on with the orange or the purple. And really, in the future, it's not going to be orange and purple. We're going to be talking about sodium ions, potassium ions, chloride ions, calcium ions, or glucose molecules. If we're talking about water molecules, and the movement of water molecules, we will not just say, oh, it's a simple diffusion, even though that would be it. We will talk about osmosis. So osmosis is just that special term we use for the diffusion, passive diffusion of water molecules. That's it. So we don't use the term osmosis for passive diffusion of sodium ions, even though osmosis is a passive diffusion. It's just specifically for water molecules. So water will diffuse across a membrane, same as any other molecule that we've seen so far, from a region, again, of higher water concentration towards a region where there's less water in the environment. So let's look at this example instead of just sentences. I'm going to use a drawing here. And let's look at, in this drawing, we have sugar molecules. The sugar molecules are illustrated in green. These are all the green dots. And if we counted the dots, the green dots, here, let me use green for glucose. Let's assume sugar is glucose. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 little green dots on this side. This is your artificial membrane. And on the other side, we have 1, 2, 3, 4, 5, 6 sugar molecule. So we actually have sugar on both sides. Well, where's the side with more sugar molecules? It would be here on the right side. So this side has a higher concentration of the solute. The solute here happens to be glucose. So there is glucose on the other side, but it just happens to be more concentrated on the right side. Okay. So if you were to be asked if there was a passive transport taking place, in what direction would the glucose molecules go towards? That would be a typical question. What's the passive transport direction here for the glucose molecules? So you see, oh, it's more on the side, on the right side than on the left side. So you say, oh, then the water molecules are going to go, the glucose molecules are going to go towards the left side, right? Because we counted all these dots, they're more on here. That's why we said it's higher concentration of glucose on this side. Okay, passive transport, we go to the other side until equilibrium. Okay, except that this particular scenario, the glucose molecules are actually not allowed to pass through because it's a selectively permeable membrane. In this particular scenario, we do not have the transporter in this membrane. So this is an artificial membrane, selectively permeable membrane, no transporter. I should write here. Oh, where did all my colors go? Oh, there we go, there we go, there we go. No transporter. So if there is no transporter, that means no diffusion of glucose. Oh, that means glucose is going to stay wherever compartment it's already in. It can't go through. It's going to stay where it is. So what's going to happen is that the water molecules are going to compensate for that setup. And the water molecules are going to move towards the compartment where they're less concentrated, because we're still going by the definition of a diffusion process is from high concentration to low concentration. So high concentration of water now, we're looking at water, H2O here. Look here, look at these two compartments. When you have less of the solute, so see, lower solutes, you basically have more room for water, right? So more water on this side because there's less solute, so there's more room for water. And where there's higher concentration of solutes, there's less room for water. So in your mind, every time you see high concentration of a solute, so it's basically a solution that's very concentrated in something, here our example is glucose, automatically think, oh, that means there's not as much water in it. So here, if we're looking at right side, left side, just here, let's put a left side and a right side. There's going to be less water molecule on the right side and more water molecules on the left side. So by the diffusion process, water here, it happens to be able to go through the membrane. Water is going to diffuse from high to low. That's the diffusion process. It's a passive transport, and it happens to be called osmosis. So here the water molecules are illustrated with these little red and white balls here. The red is representing oxygen and 2 hydrogen atoms. So what's going to happen is that water molecules are going to go to the compartment where there's less of them. And that's going to basically help dilute the glucose and compensate for the fact that glucose can't get through the membrane. And you can actually see that movement because with this particular setup, you can see the rise of water level on this side of the tubing. So this is kind of something that would be nice in a laboratory setting. It would be nice to set it up and see it. Okay, so here's some terminology that's going to be very important when we talk about concentration of a solute in a solution. So the word tonicity, so the ability of a surrounding solution to cause a cell to gain or lose water. So learn these 3 terms, and we're going to apply them to the scenarios that we just talked about. When we use the term isotonic, that means the solution causes no net movement of water into or out of the cell. Isotonic, that means the tonicity is the same on both sides of the barrier. When we say hypertonic, that means the solution will cause a net movement of water out of the cell, And the cell is going to end up shrinking. We're going to do some drawings and you'll understand it even better with the drawings. And when we use the term hypotonic, this is going to cause a net movement of water molecules into the cell. And the cell's going to end up swelling and swelling because the water is getting into the cell. And I'm telling you, these are very basic, just general definition here, but this is going to apply in physiology when water is moving inside the cell and the cell swells and now your patient is swollen. That's because there is, retention of fluids in the cells. So let's look at the example of red blood cells. If you put a red blood cell in a hypotonic solution, so here, so this is the hypotonic solution is what the cell is in, okay? So if this is hypotonic, that means inside the cell is very concentrated. So there's high solute concentration. Hypotonic, that means it's low solute concentration. So the solutes high inside the cell and low on the outside of the cell, it's going to promote water movement into the cell. Because remember, the water, if you just looked at the water where there's low solute, it means there is high water concentration. Remember, I was explaining that over here. Wherever there's a lot of solutes, there's less room for water molecules, so there's just less water molecules because the space is taken up by the solutes. And where there are less solutes, there's more room for water molecules. So when you have a very highly concentrated solution, like this solution of glucose on the right side here, there's going to be a tendency for the water to move towards that high concentrated solution. So it can dilute it because the solute themselves can't move through the membrane. So that's why the water ends up getting inside the cell, because the cell has a high solute concentration, and as opposed to the outside of the cell. So when it's isotonic and there is no difference between inside and outside, then really the net movement is going to be zero. You know, some will go out, but some will come in, and it's just really not gonna, it's gonna even out. There's really not gonna be a net movement of water. And when this solution that the red blood cells are placed in, if it's a hypertonic solution, hypertonic, hyper, that means lots of solutes. And what did I say when there's lots of solutes? Let's go back here. High concentration of solute, that means there's less room for water. So hypertonic solution, that means less water out here and more water in the cell. So the water is going to have a tendency to move from the inside of the cell to the outside of the cell by osmosis. And if that gradient is really steep, there's going to be a lot of water that's going to come out, and the cell is going to shrink. So the environment of red blood cells is really important because it's going to determine if the red blood cell is keeping its natural shape, or if it starts swelling, or if it starts shrinking, and that those two other scenarios are definitely not good. Okay. So the movement occurs if it's not by simple diffusion, that's the word we used earlier, simple diffusion just straight across the membrane, it will be facilitated with the use of a protein. So in French, facile means easy. So here, what this means is that it's going to be made easier by the protein in the membrane for these solutes to go through the membrane because they're polar, they wouldn't blend with the membrane and they'd be stuck outside. So this facilitated diffusion is to make the diffusion easier. So the passage of substances down their concentration gradient, because we're still talking about a diffusion process across a membrane with the help of a transport protein that will make this passage easier. So we call it a facilitated diffusion. So we have channels that can help with that, or carriers. All right. The channels are tunnels, and they're very specific. In general, we have a sodium channel that's just for sodium ions. We have calcium channels that are just for calcium, fluoride. Every ion has its own channel. And a very, very important channel are aquaporins. So not only are they channels for water, but they happen to have even their own special name. They're called aquaporins. And aquaporins are going to be very important in kidneys when we need to have water retention and not have so much water go out into the urine because maybe our blood pressure is dropping. And when our blood pressure is dropping, one way of increasing blood pressure is to increase blood volume. And how do we increase blood volume? We put water in blood. Where do we get the water? We can go into the urine and bring water back from the urine into the blood. And that's what happens in the kidneys, where there's constant monitoring of blood pressure and level of basically blood volume and level of water in the blood. And if those volumes drop, we need to bring water back into the blood. So aquaporins are going to be very important in kidneys to allow for water molecules to really be transported in and out of the blood through the kidney cells. And again, why do we need channels for water molecules? Because water molecules are polar molecules. We really discussed polar molecules, water molecules being polar molecules extensively. This is how hydrogen bonds are made with between water molecules, right? Between the slightly negative end of one water molecule is creating a bond with the slightly positive end of another water molecule. And this is how you end up with these sheets. Okay. Other types of ion channels. Other types of channels are ion channels, very specific for only one ion at a time. So many of these ion channels, this is something that you will see in physiology, and it's why it's important I introduce that to you here, is we describe them as being gated. That means imagine like a little door here. You see this in the illustration. This is your gate, and this gate opens. When does it open? It opens when the ligand, which is whatever specific molecule that the channel is specific for, when that molecule binds on the channel, then the channel knows it needs to open, and then it opens for a specific ions that will go through the channel. So there are two things going on, so I don't want you to be confused. The channel is specific for the passage of a specific ions, but it's also specific for the binding of a specific molecule that happens to be the ligand for that channel. So let me give you an example that's going to be really important in physiology. Is the example of a little molecule, I'm just going to say it's a neurotransmitter for now. A neurotransmitter, it's a little molecule that's released by neurons, and it's going to bind on a neurotransmitter channel. And this channel, once the neurotransmitter is bound on it, so here I'm going to show the neurotransmitter bound on the channel, the gate that was closed is now open. There we go. It opened up. And what did it open for? It opened up for a specific ion to go through. So these ions, when they see the gate open for their own channel, they're going to be so happy. They're going to diffuse down their concentration gradient. So the cell will allow for these ions that are really concentrated on one side of the cell, and they're stuck on that side of the cell. Because remember, we're at the membrane of the cell. And these ions cannot go through. They're polar. They can't just kind of seep through the membrane. They need their channel to be open. And sometimes the cell says, no, you can't get through. This is not like an open door that's like constantly open. It's just a tunnel that you just kind of go through. There's actually a gate, and you can't go through unless there is a signal from the binding of the specific molecule that this channel is waiting for. So this is how cells communicate with each other. This neurotransmitter here, this molecule, binds on the channel as a signal for the channel to open and these ions to flood the inside of the cell. And then the cell wakes up, and then the cell will do things downstream that is going to basically, here in the illustration, there's going to be a cellular response to the binding of that original ligand. Yeah, you see, so this was the gate, and the gate opened. And it will allow the entrance of these ions in. And then the gate will eventually be closed again when the ligand is plucked off of their binding site. And you'll see in the future classes how that happens. All right, so for carriers, we have basically a change in shape. I'm not going to kind of rehash this. We talked about how they literally change shape and move the solute to the other side. So no energy is required, whether it's simple diffusion or facilitated diffusion. Passive transports require no energy. However, sometimes the cell will want to move things against their gradient. Oh my goodness. It's like the solutes are going into a compartment where they're already concentrated against their gradient. So imagine you have, a classroom with 50 seats, and you're inviting and pushing and forcing 200 students to sit in that classroom on each other's lap, on top of each other, sharing one space. It's very, very going to be very, very crowded, and it's just going to require energy. You know what? A better example, if you ever take the metro in a big city, and the metros at rush hour, they're really, really, really packed, and people really want to go home, and they see all these people in there, and they just get into the metro anyway. And I'm telling you, they're going to be pushing, and it requires a lot of energy to get into that metro car and just push people just to have some room to stand in there before the doors close. It just requires a lot of energy. And that's called an active transport that requires energy to take place. And the energy is usually in the form of ATP. So these proteins that are going to be carriers in these stories, that we're going to have carriers involved, they're going to be called pumps, because they're going to use the energy to pump solutes against their gradient. So make sure you start using the proper terminology. So let's look at the sodium-potassium pump. The sodium-potassium pump, it's basically two stories in one pump. So this one pump is specific to sodium ions and specific to potassium ions. So it's going to be in charge of two different ions through the same carrier. So it has affinity for both ions. And its job is not like a sodium channel or potassium channel. Its job is to move these ions against their gradient. So if there's low concentration on one side and high concentration on the other side, it's going to move these ions towards where they're already highly concentrated. And we want to push them and push them and push them and really make sure they're very concentrated. So let's see here. We have sodium ions that are going, I'm trying to see here, sodium ions that are going to be released. Yes, okay. So here is the channel. And what it's doing, it's basically taking 3 sodium ions out, but only bringing 2 potassium ions in. And this is the membrane. And this is moving these ions against their gradient. That means that, and I'm just going to do a very big K here to show that there are more potassiums here, and maybe we can use actually a different color. I can do a highlight. Okay, so if I do a highlight with sodium ions being highlighted, I'm going to do, oops, that's not what I meant to write. Okay, so sodium ions are more concentrated outside, and potassium ions, okay, I'm kind of, yeah, let's do pink for potassium. Okay, so in pink, okay, so there's a lot of, and we can say, okay, there's a little bit of pink here, that's okay, and there's a little bit of green, oops, there's a little bit of green here. Yes, but most of them are, all the sodium ions are on the outside, and most of the potassiums are on the inside. And look at what this pump is doing. It is literally pumping them towards the area where they're already very concentrated. That's hard. You're pushing them into a space where they're very concentrated. This is not going to happen naturally. You're basically forcing them to get in there, right? You're like pushing that person into that tram car, the metro car, and it's really hard. You're really pushing them in. And this is going to require energy. And that's where ATP comes into play. So let's use red here. ATP is going to be used up. That's why I drew this arrow in this direction. To create these movements against their gradients, we need an ATP molecule to be used in the process. So here it is. There's the ATP, and it's going to be basically like it explodes, right? It's going to turn into ADP with a release of one phosphate and an ADP molecule. I don't have any more space here. ADP molecule that's released, and that just the plucking off of one of the phosphate molecule is enough energy released. So ATP is an adenosine triphosphate with 3 phosphate molecules here, and it turns into an adenosine diphosphate with one phosphate group that's going to be plucked off, and that plucking off is enough to release that energy. So I'm going to do just this for energy. Energy. Okay. All right. Sometimes the solutes are moving in the same direction, and we call this a co-transport. Co-transport is possible when the movement of substances down its concentration gradient is coupled to the movement of another substance against its gradients. So this is different from anything that we've seen so far. So something that has moved down the gradient, let me see. Right. So here's the co-transporter of hydrogen ions and sugar molecules. These hydrogen ions are moving down their concentration gradient. Why? Because these hydrogen ions, let me use black, right? H plus, H plus, H plus, right? All of these hydrogen ions are really packed up in here. So they're going to naturally move down their concentration gradient by diffusion. So this is a drive. This actually it provides the energy to pull sugar molecules also inwards here against their gradient, because sucrose, you have one here and one here, and this is only one on this side. So you're moving a substance against its concentration gradient, the sucrose, using the energy of the hydrogen ions. So how are we making sure that the hydrogen ions are going down their concentration gradient? We have a pump that makes sure to pack them up on that side of the cell. And then when the co-transporter is ready, oh, I have all the sucrose, I'm ready to bring it in. Let's open the door. And that allows for all these hydrogen ions to like literally down their concentration gradient. And that provides the energy to suck in the sucrose against the gradient inside the cell. Okay, so that's it. That was the coverage of the different types of transports, whether it's passive transport or active transport. Passive transport, we saw simple diffusion versus facilitated diffusion. And within facilitated diffusion, we saw either with channels or with carriers. In active transport, we saw pumps that requires the energy of ATP. And we also saw co-transporters that uses the energy from a down gradient movement. That's enough. That energy is enough to pull something else in against their gradient. All right, that's it about transport at the membrane. Thank you for paying attention.